So hopefully by now everybody's looking at Monday's page in our packet for this week. And you'll see from the top of the page that the topic we'll be discussing is quadratic functions. Now, quadratic might be a new word for you, but function should be familiar. So the first thing I want to do is just remind you what a function is. So you might want to write this down on the top of your page. A function is a math expression where basically you plug values in for x and you get values out for y. And we've been dealing with functions for a couple of months now. We might not have been as explicit about the fact that they were functions, but we've been dealing with a lot of different types of expressions that have x's and y's in them. We put values in for x, we get values out for y. That's how these work. So we've learned about linear functions. I'm going to zoom in. Linear functions contain just a single x. We typically write them in the form of mx plus b. But remember, m and b, these are numbers. So if we had an example of a linear function, it might be something like y equals 1x plus 1, which is the linear function in this picture, for instance. But we can get so much information about these functions without ever looking at the picture. We get the information from the function itself. The m is our slope. The b is our y-intercept. So we learned a lot of tricks about how to identify different features of a linear function just by looking at the formula. Then we started talking about exponential functions, which was our second type of function, and this was similar. Exponential functions all have a similar shape, right? It's a curve, and your curve is either growing or your curve is decaying, going down. So they had a predictable pattern that they followed, and we could tell certain things just by looking at the function itself. So exponential functions have an x value that's in an exponent, and then we could tell whether it was growing or decaying based on the base. So we knew whether it was going to be going up or down. And we also learned a little trick at the end of last week. We could find our asymptote by looking at the number that was added or subtracted at the end. In this case, there's nothing there, so it would be a plus 0. So that tells us we have an asymptote at 0. So I'm just kind of reminding you of some of the things we've already learned about different types of functions. And I want to impress upon you that in many functions, you can gather a lot of information just by learning a few tricks and figuring out where in the function to look for those little tricks. So now we're going to introduce a new type of function, and this one's called quadratic. A quadratic function comes in the form y equals ax squared plus bx plus c. Now a and b and c, those are going to be numbers. So we might have an example like y equals, let's see, 1x squared plus 3x minus 2. So instead of an a and a b and a c, we'll actually have numbers there in our functions. But these will have a different type of pattern that they'll follow. The graphs will look different. Notice this picture, it's kind of like a bowl shape. It goes up on both sides, whereas our exponential function just goes up on one side. So this is a slightly different type of pattern that we're going to be drawing on our graphs. And they start with an x squared. So linear functions just have an x. Exponential functions have an exponent that's an x. And quadratic functions start with an x squared. So we're going to need to be able to tell the difference between these three types of functions just by looking at their formulas. So let's get started talking about some more specific details about quadratic functions. So the definition of a quadratic function is they are functions that begin with an x squared term. When we write them, we list the terms in order. You always put your x squared term first, your x term second, and then finally you follow it up by the one that doesn't have an x at all. So they go in order from biggest exponent to smallest exponent. X squared, x, nothing. Make sure you write them in the proper order because that's the way that A, B, and C are listed, in that order. A is first, B is second, C is third. If you mix your terms up and you put them in the wrong order, things are going to look a little confusing. So you might even want to make a little note for yourself that the order you write your terms in is from highest exponent. Make sure you can spell highest exponent to lowest exponent. It's important that you always order them that way. So what we're going to do now is we're going to look at two different examples of quadratic functions. We're going to make a table and we're going to draw the function to see what it looks like. So let's take example 1. We're going to create a table of values and graph the function y equals x squared minus 2x minus 3. So if we want to create a table of values, the first thing we do is just come up with a few random x values. Let's try to pick some x values that will fit on this graph. So maybe like, I don't know, how about -3, -1, 1, 3, and 5? I'm choosing these values for a specific reason that you don't know yet, but generally you'd probably want to put 0 on your list. So yeah, just pick a few random x values, make sure they're values that will fit on the graph that you're given. And then what do we do with these? We have to now find our y values. So take your function, which is y equals x squared minus 2x minus 3, and we're going to go down this list and we're going to plug the x value in to figure out what the y value would be. So for the first one, we would have y equals -3 squared minus 2 times -3 and then minus 3. I didn't leave you very much room to write this over here in the margin, so try to write small. Notice when you plug that -3 in, you have to put parentheses around it. If you forgot your parentheses, you will get the wrong answer. So I'm going to make a little note here. Parentheses, don't forget these. So they're important when you're writing the problem down, but they're even more important when you're plugging the problem into your calculator. So get out your calculators. Did everybody get 12? Any issues still? All right, so when we plug in -3 as our x value, we get 12 as our y value. So our first point is -3, 12. Well, that's not going to fit on our graph. That's going to be a little bit too high. So we're not going to be able to draw this one on our graph. Let's move on to the next point. Now let's plug in -1. So first we'll write it out. Y equals -1 squared minus 2 times -1 minus 3. And we get to practice using our calculator again. When we plug in -1, we should get 0 as our y value. This point will fit on our graph. So I'm going to plot the point -1, 0. All right, for our next one, we're going to be putting in the number +1. So we'll have parentheses, +1, parentheses, squared, minus 2, parentheses, 1, parentheses, and then minus 3. So plug this in. What did everybody get? -4. Good, good. That's what I got. All right, let's do the next one. This one's going to be y equals parentheses 3 parentheses squared minus 2 times 3 in parentheses minus 3. So plug all that in. I got 0 again. Okay, interesting. And finally, we're going to put 5 in for x. So repeat everything. Go back and put 5s in instead of 3s this time. And what do we end up with? 12. Does anybody see a pattern on our table? Colin, what do you see?
So there's, you look at it, the y value seems to be appear twice.
Yeah. So like this, whoops. The 12 of the y value appears twice on this table. And in fact, the 0 y value appears twice as well. That's an interesting thing that we'll have to keep an eye out for. Let's see if we can figure out what's going on there. All right, so let's plot all 4 of these points. I already did -1, 0. Let's do 1, -4. Then 3, 0. And finally 5, 12. Well, 5, 12 is off of our table again. So what we're going to do now that we've drawn as many points as we can fit on here, if we wanted to try to draw a couple extra, like if we want to know what's going on at 0 or at 1, 2, or at 2, we could plug those in really quickly. Actually, I'm going to do that. We get -3 and 4, -4, and -3. Whoa. So I get 0, -3, or 2, -3. So these are a couple of other points that are on our table. If we connect these with a curve, kind of goes down and bottoms out and then turns back into an upward position or an upward direction. This is the shape of our graph. So there are a couple of important things I want to make sure you have on your graph. First of all, both sides of this are kind of pointing up forever. Remember the points that wouldn't fit on our graph? The -3, 12 and the 5, 12. So this keeps going. There are points way up there above on our graph. And so you need to have arrows at the top to indicate that these go on forever. They'll never stop. They'll just shoot up into the sky. The next thing I want to point out is kind of what Colin was hinting at. Notice that the y value of 0 shows up twice. And the y value of -3 shows up twice. And actually, if you pick any one of these points, this y value shows up twice. This y value shows up twice. They all show up twice. We'll talk about that more in a little while. What I'd like to do right now is turn your attention to example 2. We're going to do the same thing. We're going to model this other quadratic equation, and then we're going to compare the two graphs to each other. So in this new quadratic equation, we have a different function this time. This time we're dealing with -2x squared plus 2. And let's pick some x values. How about -4, -2, 0, 2, and 4? Why not? Okay, so we're going to do the same process. We're going to take our function, but we're going to plug -4 in first. So we'll have -2 times -4 squared plus 2. And this is what we'll plug in for our first point. So everybody practice putting this in your calculator. So what did you get, Jacob? -30. So when we type in -4 to our calculators, we get -30. Well, that's not going to fit on our graph. Let's try to find our next point. So this time we're going to plug in -2 as our x value. Plug that into your calculator.
-6.
That's exactly what I get. Perfect. So when we plug in -2, we should get -6. Very good. Has anybody already jumped ahead and plugged 0 in yet? Faith, what'd you get? +2. And has anybody plugged in 2 yet? Jenny, what'd you get? -6. Uh-oh, here's Colin's pattern. Max, what'd you get for 4? Perfect. See this? Again, we have this pattern where -30 is showing up twice, -6 is showing up twice. It's a good sign that we're getting a consistent pattern. All right, let's plot the ones that we can. -4, -30, not going to fit. But -2, -6 fits. That's down here. 0, 2 fits. And 2, -6 fits. That last point won't fit either. So this one, if we connect our points from left to right, we start on the left and go to the right, it looks like our curve kind of goes like this. Now remember to put arrows at the bottoms of these on both sides because these keep going. They don't just stop at the end of our graph. They keep going down. We just couldn't fit it on our page. All right, so we did all of that work to find all of these points and to draw them on a graph. Let's talk about these. What are we looking at? All right, take the two graphs and think about them for a minute. And let's see if we can come up with anything that the two graphs have in common. Yeah, so like all of these y values show up twice. These all show up twice, but over here, so do these. Very good. So that's something that these graphs have in common.
One way or just curving a certain way, arcs.
Exactly. So we talked about our exponential function and our linear function. Like our exponential function rises in one direction, but our quadratic function will change and both sides will go in the same direction. So it might rise on both sides, or in example 2, it might fall on both sides. That's a great thing to point out. Anybody see anything else? Yeah, Colin, keep going.
Each one has like a specific point that's just like it only occurs once, and it's the high point and the low point. Exactly.
Do you see these points here? We've got this point at the very bottom or the very top of both of these I'm using a word you don't know yet, of both of these graphs. And we pointed out a pattern where all of these values occur twice. They repeat, except for the one that Colin just pointed out. Very good. All right, there's one more thing I want to point out that these graphs have in common, and that's their shape. You know, it's not like where one of them's a star and one of them's a triangle. These have the same shape, right? It's kind of a bowl shape, like a U, right? Let's talk real quick about their differences. What's the difference that somebody can see between these two graphs? Any differences? And don't say color because I made that part up. See if anybody else can throw anything in. How about you, Jake? The first one is shifted off the center line. Very good. So the second graph, in example 2, this, oh no, I erased. This center point is centered right on the middle of the graph. But in the first one, our center point is kind of shifted over to the right a little bit. Yeah, that's a good thing to notice. Anything else? Anything that makes these two graphs different? Lincoln, why don't you take a stab at it? Can you see any differences between these two graphs? I see something that stands out. They're kind of opposites in some way. In what way are these two graphs opposites of each other? Yeah, one's pointing up and the other's pointing down. All right, so that's enough talk. Let's actually get into some heavy-duty algebra definitions. This week, we're going to be looking at a lot of graphs like this, and we need some precise language we can use to describe them. So the first thing we're going to introduce is this word parabola. Parabola is the name for the U shape of a quadratic function. Parabola is the name of the shape. It's like a U. Now it can be right side up or it can be upside down, like Lincoln pointed out. So parabolas can be bowls or they can be kind of like hilltops. But that just describes the U shape. So think about it. Every graph or every type of function has their own shape. Linear graphs have the shape of a line. Exponential graphs have the shape of a curve. Quadratic graphs have the shape of a parabola. So commit this word to memory. We'll be using it a lot. The next definition I want to go over is to the right. Standard form. We already mentioned this, but quadratic functions are generally written in the form y equals ax squared plus bx plus C. What's important about this form is by just simply looking at the function, you can figure out what A and B and C are. And we're about to see a bunch of other definitions that show us why A and B and C are important. So really quickly, we're going to go up to example 1, and we're going to find A and B and C. So if we have x squared minus 2x minus 3, A is the number that's in front of the x squared. What number is written there? 1, exactly. We don't usually write it, but there is a positive 1 in front of that x squared. So A is equal to 1. B is the number that's connected to the x. So what's B in this case? -2. I heard some people say -2. Good catch. The sign is also important. So our B here is -2. And then finally, C is the number that's just sort of added or subtracted onto the end. So what's our C? You got it. Sign again is important here. So for our very first example, our A, our B, and our C are 1, -2, and -3. We're going to do the same thing in example 2, but example 2 is a little bit tricky. So pay close attention here. In example 2, we have -2x squared plus 2. Well, we've been talking about A, B, and C. That's 3 things. But this only has 2 things. So what's missing here? C is the one at the end that doesn't have any x's. So C is actually here. We're missing our B. If there's nothing there, we call it 0. So we could even write it like this. If we wanted to visually see where it went, you could write this as -2x squared plus 0x plus 2. And sometimes that helps me just to see very clearly exactly what my B would be. So the reason there was no 0 in the original problem was because it's kind of silly to write that, right? 0x is just 0, so it disappears. But this can help you identify your A, your B, and your C. So in this example, our A is -2, our B is 0, and our C is +2. So you might be wondering, well, why do we care? What are A, B, and C anyway? Well, remember when we were dealing with lines, we had our y equals mx plus b. Well, m told us something about the line, and b told us something about the line. That's what's going to be happening here with our parabolas. So look at your next 2 definitions, concave up and concave down. A parabola that opens up, so it's like a bowl that's facing up, or in the definition here I wrote, it's like a smile. A parabola that opens up like a smile occurs when A is positive. So if there's anything on this page you're going to highlight, it should be this right here. Your parabola will be concave up when your A value is positive. So I'm going to scroll back up to example 1. The A value is this one in front. It's the number that's connected to the x squared. So it's the first number, your very first term. If that's positive, you're going to get a smile, concave up. What do you think is going to happen if it's negative? It's going to go down. So we can highlight that too. For concave down, this is when a parabola opens down like a frown. So it's kind of downward shaped and our arrows are pointing down. That's called concave down. And this occurs when A is negative. So if we scroll back up to example 2, we can see that our function started off with a -2x squared. So our A value is -2, which is what makes it concave down. And notice our 2 pictures. We had a smile for example 1, and we had a frown for example 2. So that might help you remember how to find concave up and concave down. Positive is a smile, negative is a frown. So next we're going to talk about y-intercepts and x-intercepts. You already know what these are. We talked about these with lines. We talked about these with exponential functions. With quadratics, your y-intercept has the same definition it's always had. The y-intercept is the point where our parabola crosses the y-axis. So in example 1, it would be the point 0, -3. And in example 2, it would be the point 0, 2. So the way we find our y-intercept is either by looking at the graph. If you have a picture in front of you, just look at the picture and you can find it very easily. But if you don't have a picture, here's how you find it. You let x be 0 and you find y. You plug 0 in for x. So let me show you something. In our first example, example 1, this was my starting equation. If I put a 0 in for x, this first piece is going to turn into a 0. The second piece is going to turn into a 0. So what am I left with? Just the third piece, just the -3. Well, we have a name for that third piece. That third piece is c. So when your quadratic function is written in standard form, your y-intercept is going to be c. So the y value will be c. Your x value on a y-intercept is always 0 because you're letting x be 0 and then you have to find y. Your y value will always be c, whatever that last number is in your quadratic function. So just a little tip for you there to save you some time. Now, x-intercepts are kind of the opposite of y-intercepts. X-intercepts are the points where the parabola crosses the x-axis. So I do want to point out that your function will only ever cross the y-axis in one place. But because of the feature where your function can go down and then come back up, you might have more than one x-intercept. You'll only ever have one y-intercept, but you could have multiple x-intercepts. So sometimes in a problem where it says find the x-intercepts, you might have more than one answer. Okay, so for the next two definitions, we're going to be dealing with a formula here. So this is, if you're feeling tired and you're about to pass out, this might be a good time to perk up. We've been talking a little bit about how, well, these y values keep occurring twice on both sides. That's because of the axis of symmetry. The axis of symmetry is very important. Most of the questions you will answer this week will ask you about an axis of symmetry. Parabolas can be cut in half. Take this green parabola we did on example 1. If we draw a line straight down the middle of this parabola, everything on the left-hand side of this line is going to be exactly the same as everything on the right-hand side. The left and the right have to match because they are symmetrical. You guys know what symmetry is, right? Like a face is symmetrical because if you draw a line down the middle of the face, the two sides should be the same. They are mirror images of each other. The two sides are the same. And this axis represents the middle that we could fold over to keep them the same. The axis of symmetry, though, is a line. It is a vertical line. And you guys might remember that vertical lines are always written in the form x equals blank. So make note of this. When you're trying to find an axis of symmetry, you have to present your answer in the form x equals blank, where blank is the number that x is passing through. So going back to our example, what is the x value of this axis of symmetry? What is the x value that this line is sitting on? Yeah, it's 1. Sorry, let me zoom in a little bit. It's 1. X is positive 1 here. So our axis of symmetry is x equals 1. Axis of symmetry is usually pretty easy to find when you're looking at a picture. But we won't always be looking at a picture. Many, many examples that we will do this week, we will be given a formula and we'll have to find it. This is very important. Make it so that you can come back to this very easily. Highlight it, outline it, make note of it, because you'll be using this a lot this week. If you want to find the axis of symmetry and you don't have a picture to look off of, we have to use this formula. X equals negative b over 2a. Well, what are a and b? Where do those come from? Remember the a, the b, and the c that we just talked about a few minutes ago? They come from there. So our first example, in example 1, we had y equals x squared minus 2x minus 3. That was our function that we started with. So if we wanted to find the axis of symmetry of this quadratic, we would say a is 1, b is negative 2, and c is negative 3. To find our axis of symmetry, we would let x equal negative b over 2a. But instead of plugging in b, I'm going to plug in negative 2. And instead of plugging in a, I'm going to plug in 1. Do you see where those numbers came from? You take your function, you find your a, your b, your c, and then you plug in for the a and the b into this formula. And you can simplify it. You end up with positive 2 over positive 2, which is 1. So our axis of symmetry is x equals 1. But we already knew that because we looked at the picture. Two different ways to get to the same piece of information. The picture way, the graph way, and the formula way. All right, let's go back up to our picture. So our axis of symmetry, since it cuts right down through the middle of that graph, it goes through this special point that I think it was Colin pointed out earlier. We have this special point at the bottom. That point has a name. It's called the vertex. You got it. So the axis of symmetry is a line, but the vertex is a point. So when you go to write the answer for a vertex, you better write it in the form of a point, x comma y. So the x value of the vertex will be the same as the x value of your line of symmetry, because your line of symmetry goes through the vertex. So they are in the same place. They're on the same line. They will have the same x value. So we can always start out, if we already know our axis of symmetry, we can just put that x value in automatically. Super easy, right from the jump. Then we have to find our y value. And how do you find a y value if you know an x value? You plug in your x and you get out your y. So we'll have to plug it into our function. So we would take y equals 1 squared minus 2 times 1 minus 3. And that would give us a number. We could plug this into our calculator. We end up with minus 4. So 1 comma negative 4 would be our vertex. Now, we only have to do this process if we don't have a picture to look at. If you have a picture to look at, just find the point. 1 comma negative 4, we can just see that on the graph. I'm just showing you how to find it algebraically if you don't have a picture. Okay, there's one more concept we need to address, and that is the vertex is always called the vertex, but sometimes we give it a different name depending on where it's situated. If the vertex is at the bottom of your graph, we call it a minimum. So this vertex in example 1 would be a minimum. The vertex in example 2, since it's at the top of the graph, it's called a maximum. So whether a vertex is a min or a max will depend on whether you've got a smile, concave up, or a frown, concave down.